Alright, in this video we're going to take a look at a person swinging a bucket of water around their head and do an attempt at an analysis of this. So you've probably seen this trick or whatever. The person swings the bucket around their head like this, the water doesn't fall out, and everybody says, wow, how come the water didn't fall out? Of course, the physics types don't really ask that because what the physics types know is that the water really doesn't have any natural tendency to come this way. After all, the water has inertia, so its tendency is to move in that direction, to keep doing what it was doing, to maintain its constant speed and direction. It really isn't going to do this. In fact, it's pretty lucky that it doesn't do this, and the reason it doesn't do this is because the bucket has a bottom, and the bottom of the bucket puts an inward force, that would be normal force, on the water. And that normal force pushes inward. So when the bucket's here, instead of going out like that, it gets pushed inward. And instead of flying off tangentially, it gets pushed inward. And instead of flying off like that, it gets pushed inward. So the bottom of the bucket is continually pushing the water inward. Now, if we look at a free body diagram of the bucket of water, there's our bucket. Then at the top of this loop, like this, then free body diagram, we would have the normal force from the bottom of the bucket on the water, and we would have the weight of the water, which is the earth acting on the water. Now, I drew those two different lengths. I don't really know which is longer, so let's do a little calculation to see if we can figure that out. We'll write out the net force equation. Bucket on water plus, they're both inward, so plus earth on water should equal MAC or MAR. And we can do some substitution because I want to show you what kind of measurements we would need to collect to determine which of these two is bigger. So we'll do a little algebraic substitution here. And we can see that we'll need how fast. We'll need to know the radius, we'll need to know the mass of water that was put in there, and then away we go. We can calculate these things. So let's make up some numbers here. Let's say that the speed the bucket is going is 6 meters per second, and let's say the radius of the curve or the circle is 1 meter. All right, and let's say the mass of water is, let's say, 1 kilogram. All right, so let's put our numbers in. So normal force bucket on water plus 9.8 times 1 equals 1 times 6 squared over 1. I picked nice numbers to work with. Okay, so that becomes 9.8. That becomes 36. Normal force bucket on water. And, whoops, plus. And approximately normal force bucket on water will be equal to 26 newtons. Now notice that the weight is actually right there. That's only 9.8 newtons. So in fact, at this particular speed, the normal force is far bigger. This is going to have to be something like 3 times as big as the weight vector. It really should be more like that, I suppose. And that would be to scale. Now, of course, we can change the value of the normal force by dropping the speed. And we saw that the other day in class. Now, we could continue to drop the normal force and make this bucket go slower and slower and slower. But eventually we'll get to the point where the bucket is going so slow that the only force acting on it will be the earth pulling down. The normal force will go to 0. And in fact, any slower than that, and the water falls out of the bucket altogether. All right, so if we're going that very slowest speed, we can calculate what that very slowest speed is using this same formula. All right, and so if you use the same formula, you can see the m's drop out because the normal force has gone to 0. And if you put in 9.8 equals v squared over 1, you find the velocity. That very slowest velocity is 3.13 meters per second. Any slower than that, the